Hello everybody, welcome to Honors Physics Lesson 7.3, Potential Energy. And that's not a smart idea, don't do that at home. Alright, so there's four types of potential energy that we're going to discuss in here. Of those four, two are going to have actual equations that we're going to deal with. So we'll deal with those two last, and we'll go through some sample examples, some sample problems about that. And see how those work. But let's talk about the other two. So electric potential energy, or ZPE, this is energy that is stored in a battery or other power source, like a static sweater or something like that. Then we also have chemical potential energy, or CPE. This is energy that is chemically stored in molecules of like food or chemicals like gasoline, propane, stuff like that. In most cases, the chemical energy can be burned in some way in order to give us kinetic energy. Alright, so the first one that we're going to go through that has an equation is elastic potential energy, or EPE. And this is energy that is stored in things that are stretchy or squishy, like rubber bands, slinky, springs, anything like that is going to have elastic potential energy. And there's two formulas that we got to deal with when we're dealing with elastic potential energy. The first one is Hooke's law, and that one states that the force required to stretch or smush a spring would be equivalent to the product of that displacement and what we call a spring constant. And that spring constant is really just how much that spring can be swished or how stiff that spring is. Okay, so sorry about that. So that gives us Hooke's law. The other equation that we're going to need to know is how we calculate elastic potential energy. Right here, EPE. Again, that's measured in joules. And that energy is equivalent to half of our spring constant multiplied by our displacement squared. So most of the time, we use these two formulas together. So we can use this equation to figure out our spring constant, or we can use this equation to figure out how much force, kind of go back and forth. Alright, so let's do a quick practice problem. So let's say we have Ace Ventura, and he's going to pull on a slinky with a force of 10 newtons. It stretches out to a length of 1.85 meters, and it was originally not stretched at a length of 0.35 meters. So first thing we want to do is figure out the spring constant. Alright, so our force should equal that spring constant times x. So our force is 10 newtons, and that will equal k times our displacement, which should be 1.85 minus the 0.35. And that should give us a spring constant of 6.67 newtons per meter. Alright, now that we have this, as long as the spring remains the same, that spring constant should remain the same. So the next question asks, what force would be required to stretch that slinky to a length of 2.3 meters? So go ahead and figure out what that change in length is. So we're going to take 2. Why can I not write a 3 today? The 2.3 minus 0.35. That'll give us our x. And multiply that by our spring constant. And that should give us our total force, which should be around 13 newtons. Alright, now the last question asks, how much energy would that use? Energy-wise, our elastic potential energy should equal to half of our spring constant, so 6.67, times our displacement, which is what we get over here, which is 1.95 squared. And that should give us right around 12.7 joules. Alright, the last type of potential energy is gravitational potential energy. This is a big one, and what we're dealing with is the object has a certain height, and because of that height, it has stored energy because it could fall from that height. So anything that has a height is going to have gravitational potential energy. Now the trick here is that when we're plugging in our acceleration of gravity, we're going to use a positive 9.8 rather than a negative. Right? That helps us deal with the whole height problem because you can really measure things from the top down, from the bottom up, or from the center of the Earth. Alright, in most cases, that potential energy then gets transferred into kinetic energy. Alright, so let's go ahead and try a problem here. So let's say we have Sally and Billy Bob, and they're on a date. Ooh! And they're at a certain height, which is 4 meters. And they have a mass of 90 and 40 kilograms. Find their potential energy. Alright, so what we're going to end up doing is we're looking for the total potential energy. So let's take 90 plus 40. And I can also take them separately and then add them together, or do them separately. Let's do them together. So 90 plus 40 times 9.8. Remember to keep that positive, times our height, which is 4. And that should give us our potential energy of 5,096 joules. Alright, now taking that one step further, let's say we have Toothless Joe, and he's sitting in 3 rows above them. What height is he at, considering that his gravitational potential energy is 7,200 joules? So 7,200 should equal his mass, which is 120 kilograms, times 9.8 times the height, and that should give us around 6 meters. Alright, so big takeaways here is you can have an object that has more than one type of energy at a time. So if we add all of that up, chemical, electric, gravitational, elastic, that would be our total energy. Our total mechanical energy is all of the energy that we're going to be looking at that's actually doing stuff. So that includes gravitational potential energy, elastic potential energy, kinetic energy, and rotational kinetic energy. Now we're not going to talk too much about rotational until we get into angular momentum, angular motion. But again, I want to keep that in there because it's part of the mechanical energy. So remember, you can have both at the same time. If we take a look at an airplane, that airplane is in the air, and that means it has gravitational potential energy, right? And it also has kinetic energy because it's moving. It probably has elastic potential energy from the landing gear or from the seats or, I don't know, something else that's in there that's squishy. And it can have rotational kinetic energy like in the wheels or the steering wheel or something that's in there. Maybe a cart is being pushed back that has rotational kinetic energy. We would add all of that up to figure out our total amount of energy. Alright, it's been fun. I will see you later. Thank you for stopping by.